Hello folks, so today I don't have any questions of any year with me. I simply am trying to deal with a theoretical topic, which is the case of springs in series and parallel. So we simply want to know, actually it is the demand put up by students to deal with this theory when I posted problems related to this thing. So they actually wanted to know the theory first before even trying to solve those problems. So that's why I'm addressing that problem. And actually, it was something that I should have done previously, because first theory and then only problems. But because of that exam pressure, I first did the problems, and now in my leisure time, I'm doing the theories. So first of all, a spring is always something that follows Hooke's law, Robert Hooke's law, which we state as the restoring force is directly proportional to the extension. So which gives us F is equal to minus Ke, where the constant K is called as spring constant, spring constant. Normally it is called as force constant, but in case of spring it is called as spring constant. And the negative sign is to denote that the force is of restoring type, or this force tries to bring the body to its original dimensions. And this spring constant actually measures this spring constant with K, which we call as, it actually measures the stiffness of the spring, or I can say toughness of the spring, So more the toughness of the spring, so more tough is the spring or more stiff the spring, K is more. And if it is lax or if it is loose, if it is very soft, then K is less. So K more means the spring is stiff or tough, and K less means it is soft, I can say, or I can say it is very lax. Lax means loose, in other words. So, and this rule is followed till a certain limit, which we often call as proportional limit. Actually, not exactly Hooke's limit, not exactly elastic limit, but it is the proportional limit or the Hooke's limit. Now, when we connect springs in series, So my topic first will be springs in series. So when we connect a spring in a series, somewhat like this. So this is the left boundary. So I have one of the spring like this, then another spring like this, and then I have something that applies force here. So this spring has a force constant K1. This has got K2, K1 and K2. So when I apply force like this, since this is the single chain, the force along all the portions of the spring is same. So for first spring also the force is F, and the second also the force is F. So now we have force is same for both. This is equal to K1 is its constant for first spring. So force is same, K1 is different, so I must have this thing also should be different. So this is extension E1 is the extension for the first one, and for the second I must have F equal to K2 E2. It's because force is same, and if K1 is different, this E1 E2 should be different for each of these things. So what I will have is, if I equate these things, I will have E1 is equal to F by K1 and E2 is equal to F by K2. So therefore, if I add them, I will have E1 plus E2 is equal to F by K1 plus F by K2 equal to F common, then 1 by K1 plus 1 by K2. Now what I have now is, so when this spring E1 extends here and E2 extends here, the total extension E will be equal to, it should be E1 plus E2, because the extension will definitely add up since they are in the same chain. So I must have, so if I use this value over here, it will be F, then 1 by K1 plus 1 by K2, which then gives me E by F is equal to 1 by K1 plus 1 by K2, and I change this into 1 by F by E. Now for the whole spring, if I consider this as a single spring, I must have the force is equal to total K, this is K total into the extension total. So I must have this F by E should be equal to K total. So if I use this thing over here, I must have this is equal to 1 by K1 plus 1 by K2 should be equal to 1 by K total. 1 by K total. So that means what we now have is in series combination we have reciprocal of total force constant, total force or spring constant, constant is equal to sum of reciprocals of individual force or spring constants, So if I now want to find the value of Kt itself, I must have, so if I take its LCM, it is a K1 K2 and it will be K1 plus a K2 and equal to 1 by Kt, which will give me Kt is equal to K1 K2 by K1 plus K2. So this will be the expression for the total, which is it is an arrangement such that we don't have to go for all the calculations during numericals. Now with this value, what I can have is this K total is always less than K1, and this K total is always less than K2. So in such type of equations, this total thing will be always less than the individual things. For example, if I use a value, for example, K1 is equal to, I can prove this. So if I use a value K1 equal to 6 and K2 is equal to 3, this whole thing gives me this K total is equal to 2. So this 2 is less than 6 and this 2 is less than 3. So it's obvious. So it means that now, so this K total less means that the spring now becomes, so this makes the arrangement, less tough or more lax. And if this K decreases, and also this decrease of K means that E will be more. So the extension will definitely be more compared to the individual, as you can see from here. So initially it was E1 or E2, and in total it will be equal to plus. So the extension is more, K is less. So this is for series arrangement. Now if we do the same for parallel, so what we now have is, so let's write the topic here, springs in parallel. Now in parallel arrangement, what we have is the diagram will be somewhat like this. So this is the top support. So I have a hook like this. So from here I have the spring here, from here I have another spring here like this, then this, and here I apply the force. And the spring constants are K1 and K2 So what happens here is the extension of both of these things should be same. When I pull this, both of them come to the same thing. So E is same for both. But what happens is, since there are two paths here, the force will be different in the two branches. Depending on the constants, the force will be different. So we have the forces are F1 and F2. So F1 will be equal to, so here it is F1 and here it is, let us say, F2. So F1 is equal to K1 into E, and F2 is equal to K2 into E. And here what we have is these two forces make up this force. So I must have this F should be equal to F1 plus F2, and that's equal to K1E plus K2E, and that's equal to K1 plus K2 common, and then E. So if I have, let us say, this K total here, for the whole thing, I should have F is equal to, if I consider this as a whole spring, then F equal to K total into E. So therefore, when I compare this thing with this thing, I will have K total is equal to K1 plus K2. So here, the expression is K1 is equal to K2 equal to K1 plus K2. And it means that our this K total should be equal to more than K1, and it should be more than K2. As given by the mathematics, it should be more than all the individual values. So that means this arrangement will now be, this arrangement now becomes arrangement now becomes, now will be more tough or stiff, more tough or stiff, and the extension will be less, and the extension will be extension will be less. Now we often use these things in designing several seating arrangements. For example, in sofas of old days, we used to have wooden platform here. They used to have lots of springs like this, lots of springs like this, and then they will use foam here like this. So what it makes happen is equal to, it increases the toughness of this thing so that it doesn't collapse fully when people sit, which we often call as a springiness. Actually, we call it as springiness, or we call it as some sort of flexibility, somewhat like that. Now, with the knowledge of these things, we can combine them in several ways. To find the constant of several arrangements. For example, if I have an arrangement like this, so this is a parallel first, parallel like this, parallel, and this thing is in series with this thing. So this is a K1, this is K2, and this is K3. If so, what I must do is, first of all, I have to calculate this thing. Let us say this thing is equal to K prime. Then this is equal to, I'll have this is equivalent to a spring with a constant K prime, and then it is in series with this K3, and this is equal to K total. So this is K total. So from here, our K prime is equal to, K prime should be equal to K1 plus K2, as we have done just here, and our K total now will be equal to series of K prime and K3. So this will be equal to, as we have done in the previous expression here, so is equal to, in place of K1 it is K prime, so it is K prime K3, so K2 K3, then we have K prime plus K3, that's equal to K prime is equal to K1 plus K2, then this is K3, and here I have got K1 plus K2 and then plus K3. So this is the total expression. And now next is if I have an arrangement like this, so one spring here, another spring here, and then another spring here. So if I action like this, so this is a K1, this is K2, and this is K3. So first of all, let us know its combination. Let us say it is K double prime. So this arrangement is just like, so this is the spring here, this is the spring here. So this spring is a K3 and this is K double prime, like this, and then it's equal to the total is like this. So I nearly drew a resistor here. So this is K total. So the series of this thing is equal to, so K double prime should be equal to K1 K2 by K1 plus K2, and this K total is equal to K double prime plus K3, because in parallel. Here it's in series, so this formula, and these two are parallel, so this formula. So K double prime is equal to K1 K2 by K1 plus K2 and then plus K3. So with these things, with these derivations, or with these works, we can find the spring constants of many other things. So this is the basic steps, and complex steps then follow later. Thank you.